My name is Adrian Celaya. I'm a PhD student here at Rice. And today I'll be talking about using deep learning-based methods for inverting 2D gravity maps for the purposes of monitoring 3D CO2 plumes in the subsurface. This is part of the work I did at Total Energies last summer with Yen Soon, Bertrand Danel, Mauricio Raya, and Anthony Price. And before I go any further, just have to give you some copyright disclaimers, so I'll leave this up here just for a few seconds in case anybody's interested in reading that. All right, so to summarize what I'll be talking about today, I'll start with a problem overview, and then I'll discuss some of our deep learning-based methods for actually doing this inversion we're talking about. The first one is going to be a purely data-driven deep learning approach, and then the second method we present is going to be a combination of this deep learning-based approach with traditional methods. And then if we have time, we'll go ahead and talk about some extra experiments we did concerning sensor resolution for our gravity data, as well as changing our inversion targets from density to saturation, and then conclude and go into some future work. All right, so to give you a problem overview, I want to direct your attention to the image here on the bottom left. And I want you to imagine a scenario where we're pumping CO2 into some formation, and over time, the CO2 is going to displace something, in this case, say water. And as a result of that displacement, you're going to have some kind of change in density, right? And we can represent the location and some of the properties of this plume by that density difference right here. And now say, because of this density difference, we want to go ahead and compute the change in surface gravity as a result of it. We can do that pretty easily by applying Newton's law of gravitation. And applying this closed form equation to this CO2 plume here, we can compute the change in surface gravity data here, which is the image on the right, and that's, again, it's a 2D representation of that. And one thing to remember about this is that this forward operator is extremely well understood. It's easy to compute, and we can pretty much say all we want about it. However, if we want to go from our 2D surface gravity map into the situation where this is all we have, this inverse problem is much harder to solve than our forward problem, right? And it's traditionally done by minimizing in a least squares or L2 sense the forward operator applied to a predicted surface gravity, predicted subsurface model minus the observed, and we minimize that. And if you're familiar with, say, seismic methods, our forward operator here would be the wave equation, and then pick your poison for your inverse problem, right? So what we're interested in today is understanding how deep learning can be applied to this inverse problem. And the reason we're interested in that is because traditionally this formulation of the inverse problem, if it's not properly constrained, can give you pretty bad results. And even in that case, the results tend to be smoother and give you lower density estimates in the actual subsurface model. So again, we're interested in quantifying how accurate can we get a deep learning-based method for this, and then can we understand from a computational perspective what are the constraints and limitations of doing this. And just to take a step back, the whole reason we're even interested in something like this is because gravity data is cheap to acquire, right? If you can really understand and create a robust method for inverting this, right, you potentially have a very useful tool for monitoring CO2 sequestration sites. So now that we have an overview of the problem, I'm going to go ahead and talk about the workflow we apply for this deep learning-based approach. So to start, we're going to generate some synthetic CO2 plumes via a fluid flow simulator. We'll then take all of these plumes that we generate, apply the forward operator to create the corresponding gravity maps. We'll formulate a loss function to minimize during training. We'll actually design and build out our neural network, select some hyperparameters, and then finally get create some metrics or select some metrics to assess the performance of our inversion method. So to start by generating our CO2 plumes, we're going to use geostatistics simulation of the Johansen Formation, which is located off the coast of northern Norway. And from this, we're going to generate 500 realizations or instances of this formation that all differ in terms of porosity and permeability. And then from there, we're going to run a 500-year fluid simulation to pretty much create these plumes. And this simulation, we're going to start with a 100-year period of injection, after which injection stops, and we have a 400-year period of migration. And just to give you an illustration of what this looks like, this plume on the bottom left here is what it looks like after 99 years of injection. And then if we look at the bottom right here, it's the same plume, but after injection ends, plus 400 years. Right, so we have 500 realizations. We generate 500 different time steps. And what we're going to do is select at random a time step from each of these simulations, right? For the first 100, we're going to select time step from the first 100 years, and then for the remaining 400, we'll select time steps from across the entire 500-year period. And the reason we do this is just because for this particular application, we are interested in this first 100 years in our particular case. And what this results in is a set of 500 physics simulated, realistic looking, fully 3D CO2 plumes, which we can use as labels for our neural network. The next step in our pipeline is then going to be taking each of these CO2 plumes, applying our forward operator, and out comes a bunch of 2D maps. And these 2D change in surface gravity maps are going to be the input to our neural network. And so now for the neural network, right? So we're going to basically piggyback off the very popular 3D UNet. It's gotten some great results in a wide range of applications from medical imaging to all kinds of physics-based problems. So the thing you need to remember that we're doing here is we're mapping a 2D input to a 3D volume, right? So to start this network, if you go from the left, we start with our input. We run this through a few convolutional layers just to extract some extra features from this. And then the trick here is we're going to take a pointwise convolution layer to expand these 2D features into one big 3D volume. And this 3D volume is going to be the input to the standard 3D UNet we have right here in the middle of this diagram. And then a trick we apply here is at the end, we're going to split the output of this network into two separate branches. One is a regression branch, which is responsible for actually predicting the actual density values inside of this plume. And then the second branch is the segmentation branch, which solves a simpler problem of just segmenting out this plume or finding where exactly in a voxel by voxel or pixel by pixel case where this plume is, right? So apply a value of 1 where a plume exists, 0 otherwise. And then the last thing you'll notice is at the bottom of our neural network, we basically have a third branch where we take these low resolution features and try to reconstruct them to create the original input. And now this trick is called autoencoder regularization. And this is actually a very popular trick used in the medical imaging community, and it's been used to achieve a lot of great state-of-the-art results. And the last thing I'll say about this architecture for now is, right, this splitting technique that we applied here, we really learned from some of our earlier lessons when applying this on simple 2D cases where we're trying to invert a 1D map to a 2D map, and found that it really did improve our results over just having a single regression branch. All right, and so now that we have our network, we'll formulate our loss function. And really our loss function here is just going to be a loss function that composes of the losses for each of the 3 different branches. For our regression branch, we'll use a simple mean squared error between the true density model and the predicted subsurface density model. For the segmentation branch, we're going to use what's called the dice loss function, which is just a way of comparing two binary structures. We'll go more into detail on that later. And then for the autoencoder branch, we'll again use the same mean squared error metric that we used, but at this time we'll be comparing the reconstructed input to the true input. And then finally, our total loss function is going to be a weighted combination of these 3 losses, where we apply a weight of 0.7 to our regression loss, 0.25 to our segmentation loss, and 0.05 to our autoencoder loss. You might be thinking, oh, why these numbers? Well, we did a partial grid search during early experiments and found these particular numbers to be optimal. And then before we get into training and results, let's talk about how we split our data set and select our hyperparameters. So for a test set, we're going to take 10% of the image label pairs. Those are going to be fixed as an independent test set from here on out. And then from the remaining data set, we'll take 5% as a validation set to run during training. And what that leaves us with is a set of 420-ish image label pairs that we can actually use as a training data set. And then as for our protocols and hyperparameters, we'll select the atom optimizer, set the initial learning rate to 10 to the minus third, use a cosine learning rate with warm restarts. We found this one actually did really help a lot with training, and then select a batch size of 8, and all other hyperparameters are left at their default values. All right, and then, all right, sorry, last thing before we get into some training and results is the metrics we actually pick do matter here, right? So the first most obvious metric we'll pick is the model misfit, or right, what's the average difference between our true and predicted density maps, and this is going to be measured in kilograms per meter cubed. The second metric we're going to do is data misfit, which is really the forward operator applied to our true model minus the forward operator applied to our predicted model, and we're going to see if really this prediction gives the same gravity response as the original one. And then the last two metrics we pick are R squared and dice. Right, R squared is going to be applied between the true and predicted density models. And again, as a reminder, if you're not familiar, R squared ranges from -1 to 1, with 1 being a perfect prediction. And then lastly, for the dice, which is going to be a measure of accuracy for the actual segmentation results, we're going to apply basically 1 minus our dice loss here. And as a reminder, dice ranges from 0 to 1, with again 1 being a perfect prediction. So when we actually sit down and apply all these methods to our data set and train them, right, it takes about 4 hours to converge for about 650 epochs, and we split this across 4 NVIDIA A100 GPUs. And here, this image on the right, we have the train loss in orange and the validation loss in blue for all of our constituent loss functions. And the important thing to note here is that all of these appear to show a converging pattern, which is exactly what you want to see when you're training these models. And what it tells us is that, yes, our model was able to learn a mapping from this 2D surface gravity input to a 3D subsurface density model. So what do these actually look like, right? So if you focus on this left column, we have 2 ground truth CO2 plumes that we ran through, that we produced through our simulation. And then on the right, we have the reconstruction from our deep learning model. And again, I'll leave these up here for a second before I go into them, just so you can take a look at them. And we're seeing some good behavior here, especially on this top one, right? We're starting to capture some of this detail in the middle, and even capturing the small migration path that we're seeing going up this part of the reservoir. For the bottom one, we have that we're actually capturing this buildup of CO2 along the reservoir edge. But we do have some mismatch shown right here between the simulation and the actual prediction. As for our metrics, right, here we are. For our 50 selected independent test set points, right, we compute the statistics for all of the metrics, which are given here. Leave these up for a second. We're going to go ahead and do a comparison with this later. And again, just as a reminder, for mean squared error, we want these to be close to 0, and these we want them to be close to 1. So moving on. The next experiment we run, again, just with this particular data set, is running a 5-fold cross-validation. And so what that really means is we're taking 20% of our data as a fixed test set, running the same procedure with the remaining data as a training set, and we iterate this until we have test time predictions for all 500 models. And you can see here that these results look almost identical to what we had earlier, and that's a very good sign. It tells us that our model is robust to different perturbations of our training set, and is just another measure of robustness here. So one of the original questions we asked was, well, how does this compare to L2 inversion? And here we can have a comparison where we run L2 inversion on the same 50 independent test points versus, again, the same test points we're running for our deep learning model. And again, when I mean L2 inversion, I just want to remind you we're solving this particular inverse problem. And here we have the metrics for that, and we have the metrics for our deep learning model. And we can see that in terms of the actual density model misfit, we're winning with our deep learning model. But you'll notice here that for data misfit, L2 traditional inversion is winning on that. And the reason that happens is because we're specifically minimizing for that in our L2 inversion, whereas for our deep learning models, we're minimizing for model misfit, or actually trying to minimize the error in the densities. So just before we move on, just want to show you a comparison where, again, we have the ground truth here, our L2 inversion predictions, and our deep learning predictions. And you can see here, right, we have kind of slower, smoother density values appearing here, whereas we kind of have a little more detail appearing inside of these deep learning-based predictions. All right, so from a computational perspective, L2 inversion is still pretty cheap to run, right? It doesn't require any training data, can run out of the box, but you need to run it for every particular instance that you have. From a training perspective, it takes about 4 hours to train our models, but from an inference side, point of view, inference is extremely fast with these deep learning models, taking way less than 1 second to run a single prediction on 1 GPU. All right, so what we have seen so far is that our deep learning-based predictions do better with model misfit, or actually predicting the density values, whereas L2 inversion does a better job of actually fitting the observed data to the predicted data. So we figured, okay, how can we combine these approaches to draw on the strengths of each of them to basically come up with better inversion results? And what we'll do is take our deep learning predictions and then give that as the initial guess for our L2 models. And using this kind of post-processing based approach, we can see that we further reduce the model misfit and actually get our data misfit down to 0 in this particular case. You'll notice the one metric that doesn't seem to improve is the dice score, and the reason for that is because L2 inversion tends to add some small non-zero values throughout our reservoir mask to basically make up for this mean squared error loss in our gravity maps. And so when you actually apply a threshold, you'll get a lower value. But we can apply a small threshold to these predictions to increase this, but it comes at the expense of our data misfit. But that's that. And again, just showing you our predictions from a qualitative point of view. We have, again, our ground truth, our L2 predictions, the same pure deep learning-based predictions, and finally, our combined method prediction. You can see that in this particular case, we get rid of these small errors that we have up here and keep a lot of the same level of detail as we do in our deep learning-based predictions. And I'll leave these all up here for just a second for you guys to take a look at them. All right, so last couple experiments we run is, at this point, we basically assume a 500-meter spacing of our grids, of our sensors at every point on our surface. And that would basically correspond to this map. But we figured, okay, how does this method, how does our pure deep learning-based method react to different sensor resolutions? So we try coarsening our maps to sensors placed every 3 kilometers and increase that resolution to sensors placed every 100 meters. And what we'll run, and then we'll run the same methods on this data set, this data set, this data set, and so forth, and compare the results to get a sense of how robust our method is to this kind of data. And here we have the results of that. And what you'll notice, I know these are a lot of numbers, but just notice how similar they are across the board. Right? What this is telling us is that our deep learning-based is robust to different sensor resolutions. And this could be a potentially huge result when you're trying to design these sensor grids and save on a lot of cost if this is something that we try to do. The last thing we want to try before we conclude is, up until now, basically, we tried density as our inversion target, right? What happens if we swap density out for saturation? And again, we apply the same methods and procedures, and here's the result for saturation. And you can see they're pretty good. Similar R squared, very good mean squared error in terms of saturation units. The dice does suffer a little bit, but can probably be increased with some more tuning. But overall, we can see that our method can easily swap out different targets with little to no effort and no changes to the underlying method. Again, we'll just conclude here by saying that our deep learning-based approach, is more accurate in terms of model misfit by itself, can perfectly match the data when we apply it with L2 inversion, is robust to different sensor grid resolutions, can easily be modified to other targets, but comes at a computational cost that requires GPU and training, and as well, we do need to do some more work to understand generalization and uncertainty quantification, which we can work on later. And so, skip this for now. This work was submitted to IEEE Transactions on Geosciences and Remote Sensing. A preprint is available on arXiv, as well as some more implementation details of the actual network are available on GitHub. And pending any questions, that concludes this presentation, and thank you very much.
Thanks, Adrian, and nice job being on time. You're early. Do you have any questions?
Mark Roberts from TGS. So if I understand correctly, you're modeling injecting CO2 in the reservoir,
Yes.
and then recovering that.
Yes.
So the whole point of monitoring is to understand if your model's wrong, right? And so you really want to understand if your CO2 actually is going in your reservoir. Mm-hmm. And have you tried running a scenario where you have CO2 injection out of zone, for example, that wasn't captured by your forwards modeling? And were you able to detect that? Because that's really what you're trying to understand.
Yeah, so no, we weren't able to do that in this particular case, right? Just having some trouble modeling some of those extra external variables there. Yeah, just based on these results, I'm pretty confident it would be able to, but no, we haven't been able to do that yet.
The point is the scenario is one that you haven't thought of, right?
No, we thought of that. It's just right now we just weren't able to get a chance in the short time we had to work on this to actually get some good data on that. Yeah. So.
Hi, Mario from Hofer Institute. Thanks for a nice talk. I have a question. You tried an input and then a double output and an autoencoder regularization, but I guess that you also try a single output or two output and then the autoencoder regularization.
Yeah, we tried different perturbations of that.
Could you comment about that? Did you observe a considerable improvement when you tried that?
So yeah, I mean, one of the early improvements that we saw was splitting that output at the end of the network from just regression to both segmentation and regression really did help a lot in terms of how much data we actually needed to apply to this model. It kind of reduced that a little bit, and just the quality of the results improved dramatically with less data. So
It improved then?
yes, by a lot, yeah.
Okay, thank you.
Thank you. Very interesting talk. Thank you. I know probably about, I know very little about seismic, but I know quite a few things about reservoir simulation. So my question is going to be more on the reservoir simulation side.
Okay.
It was hard to tell from the color scale from where I was sitting, but do you have a density increase eventually over time?
In this particular case, the assumption for this simulation is it's reservoir water, and water is being replaced by CO2, so you have a decrease in density over time.
So no dissolution?
Not that I'm aware of, no. Wasn't super involved with this actual reservoir simulation. That was another colleague of mine, so if you could, I could probably get back to you on that question.
Okay, I'm asking because that is a very important capture mechanism, right, in CO2 storage. And I'm very interested to see if you'll be able to capture those things and see when you will get the convection going for an increased dissolution rate.
Okay, yeah, I'll have to get back to you on that one, though.
Okay, thank you.
Probably got time for one more question.
Hi. I have a question for you. Since you were putting constraints on the losses for the machine learning, given the smoothness of the expected results, have you tried like a smoothness constraint on either both the typical inversion or the machine learning based?
Yeah, so there was some constraints placed on the actual L2 inversion. Didn't have time to go into them today. As for the machine learning stuff, yeah, we didn't really apply any smoothness constraints on that yet, but certainly an idea worth looking at.